Our lesson today is on hybridization. And so before we define hybridization, let's just think about some things sometimes that we hear the word hybrid mentioned in everyday life. Like you might think of a hybrid car, for example, where they have a blend of different types of fuels, maybe electric and gas powered. You might think of a hybrid plant where they've taken characteristics of two different plants, two desirable characteristics, and they've spliced them together and they've grown a plant that has characteristics of both um, of the originals. If you think about even your pet, maybe you have a hybrid pet. Like now they're making these specialty breeds like Labradoodles, where they mix a purebred Labrador and then a purebred poodle and make a Labradoodle. These are all examples of hybrids. Well, in chemistry, hybridization is when you have a mixing of atomic orbitals to make new molecular orbitals. Hybridization means you have a mixing. Now, when we talked about atomic orbitals, we specifically talked about your s, your p, your d, and your f orbitals. Well, specifically with hybridization, we're going to start off with looking at how our s and our p orbitals mix or hybridize, if you will. If you think back to our last unit, we learned about our s orbital. We said it had one orientation, so we drew a box to represent a subshell or his one orientation. And if you recall, we also said the p orbitals had three subshells or three orientations. So we drew three boxes for the p orbitals. The d's had five and the f's had seven. We're going to focus on our s and p's now, as I said earlier. Now, remember, an orbital can hold a maximum of 2 electrons, and they must fill in with opposite spin. We've been learning how to draw Lewis structures and classify their VSEPR shapes of molecules in this chapter. And remember that all of the atoms, in order to get stable, they want to get a full valence shell. And what that means is if you're hydrogen, you need 2 electrons in your valence shell. But for all the other atoms, they want to get 8 electrons in their valence shell because they want to get an octet of electrons. Well, if you consider just an s orbital, an atomic orbital, it only holds 2 electrons, so there's no way that you can get 8 out of that. If you look at the p orbital, it only can hold 6 total electrons by itself if you fill every orbital up. So what happens so that the atoms can get their octet is they mix their s and their p orbitals. So they come together on equal energy, if you will, and they hybridize, or they mix. So here, if you look separately, it's 1, 2, 3, 4 total boxes. So this is going to represent the sp hybrid orbitals. So there's one of the boxes come from the s orbital, and the other 3 boxes or subshells come from the p orientations. When you have a blending or a mixing of atomic orbitals to make new molecular orbitals, this is called our sp hybrid molecular orbital. Now, I'm not going to get into all the dirty details of exactly how hybridization, the theory behind it, if you will, because what y'all need to be able to do at this point is just figure out what the hybridization is around a particular atom. So really all you got to be able to do to figure that out is to count to 4, and I know all of y'all can do that. Now, instead of counting to 4, 1, 2, 3, 4, we're going to count this way. If you start on S, then you say P1, P2, and P3. S, P1, P2, and P3. In a second when we do examples, this will make much more sense, but just keep this in mind. So there are 3 hybrid types that we need to be familiar with: SP1s, SP2s, and SP3s. Now you can't just say here SP for the SP1. In the second column here, you'll see where I have mixing, how many are mixing, and what type. So in the sp orbital, you're mixing one of your s orbitals and one of your p subshells. That's 2 total orbitals. Think of these subshells as like rooms in a house. So like there's 4 total rooms down here. 1, 2, 3, 4. If you utilize only one of your s and one of your p orbitals, we call that a sp orbital. So if we count to 2 in our examples, we'll go sp, and we'll stop there. That's 2 total orbitals are being used. For the sp2, you use one of your s boxes because that's all you have, one s box. And you're going to be using 2 of your p orbitals. So 1 plus 2 is 3 total orbitals. So sp1, p2 will be using 3 of your subshells. If we count to 3, we're going to count sp1, p2, and we'll stop here. We would say that's an sp2 orbital. For the sp3, you mix the 1s and all 3 of the p boxes to give you 4 total boxes, s, p1, p2, and p3. So if we end up counting all the way to 4, that's called a sp3 orbital because one of your orbitals comes from the s and the other 3 come from the p. Now to get your bond angles around these atoms that will be determining their hybridization, you have to go back to your Vesper shapes that we learned about yesterday. Remember, linear is 180, bent would be 105 degrees. If it's trigonal planar, 120. If it's trigonal pyramidal, 107. And if it's tetrahedral, 109.5. So if you're trying to figure out hybridization, first of all, I must tell you which atom to look at or which atom that I want you to find the hybridization of. You're going to count your single bonds, your double bonds, your triple bonds, and your lone pairs once. So really, you're counting to see how many sides of the atom has something on it. Now, I always say, think about the atom that you're looking at as if it was in a little square box. So a square has 4 sides. So if there's something on 2 sides, you would count to 2, sp1. If there's something on 3 sides, sp1, p2. And something on all 4 sides, sp1, p2, p3. So you're just going to count and see how many sides of the atom has something on it, and then you will count either sp, sp1, p2, or sp1, p2, p3. So let's look at our examples here. I want to know what are the hybridization and the bond angles of each. So here we have a water molecule, H2O. So if I wanted to know what is the hybridization of the oxygen, well, let's look at oxygen and think about how many sides of oxygen has something on it. You have a lone pair here, there's 1. You have a single bond here, there's 2. You have a lone pair here, there's 3. And you have a single bond here, 4. So all 4 sides of the oxygen have something on it. So we're counting to 4. So you would say S, P1, P2, P3. This is sp3 hybridized. Now to get your bond angle around the oxygen, you're going to go back to your Vesper shape. So this molecule, the Vesper shape, would be called angular or bent. So you got to just memorize the corresponding angles. If it's angular or bent, it's going to be 105 degrees. All right, let's try the next one. Carbon. Look at the carbon. He has 1, 2, 3, 4 sides with something on it. Again, there's 1, 2, 3, 4 sides. So sp1, p2, p3. He's sp3 hybridized. And this is a tetrahedral molecule, so you would say the bond angle is 109.5 degrees. Again, your bond angles come from the Vesper shapes. All right, let's look at example C. We have boron tri hydride. So look at your boron. We want to know his hybridization. We have something on 3 sides. So S, P1, P2. So you would say SP2 is his hybridization. And the bond angle, because this is trigonal planar, that's right, you'd say 120 degrees. Hopefully you got that. All right, and the last example on this slide is for diatomic nitrogen. And since both nitrogens are technically identical, I'll just say we're looking at this nitrogen here. So this nitrogen has a lone pair here, and has a triple bond here. So again, how many sides of the nitrogen has something on it? 1, 2. So that means we're just counting to 2. sp1 is your hybridization. sp1. Bond angle is 180 because it's linear. All right, let's look at the next here. This is our last example, and it's on your notes. So here, this is going to be more like what the question will look like on our unit test. I'm going to give you a hydrocarbon, and I want you to figure out the hybridization in the first blank, and in the second blank, bond angles.